All right, welcome back. So in the last video and the one before that, we were talking about one sample t-tests and sort of why we use them, how we use them, why they're special, whatever. And in this video, we're going to be doing a very similar process. All of these things are related, which is beautiful. We're going to be doing what's called a two-sample t-test. And you can imagine it's a little different than a one sample in that we've got two samples. Duh, right? Big friggin' whoop. Oops. So this is more commonly known as an independent samples t-test or just an independent t-test. You can call it a two-sample t-test, whatever. The big deal here is that we're testing two means. We're testing the straight up difference between maybe mean 1 and mean 2. Right? We got two groups. That means we got two means. We want to find the difference between those two and see if we can't elevate that back up to the population. All right? That's the goal with statistics, right? Now, this is going to be the more like classical side of statistics and very much the classical side of research when, you've got two groups. Let's say X1 represents group 1. It's got this many people, whatever, 3 people. X2, right? Same kind of deal. This one might have 4, right? Whatever. This group here might be like a placebo. We don't do anything to them. But this group may get some kind of drug, right? And assuming that, these two groups and the people within are relatively the same, right? That's a big deal. We're really looking at the effect of something, right? Looking at the effect in this case of some kind of drug, right? But we're getting into the idea of like classical research, right? Which is super great. And so you'll see this test. Let me move on. Actually, you'll see this test used all the time, right? So it's very important that we understand how the nuts and bolts of everything is working and how all the gears are turning together. You'll see this one fairly frequently. You also see a paired sample t-test pretty frequently as well. These two are the most common. This one is fine. This one is fine. Pretty easy to do. Not too big of a deal. But it turns out that these two are pretty tightly related. We kind of need the logic from this one to do these two anyway. So anyway, that's why we introduced that. But now we'll be really getting into it. Okay. Not that we weren't getting into the last one, but this is probably the most commonly used type of inferential test when it comes to two samples, right? Okay, all right. So, new thing, new world, got some new stuff, right? Well, not too new. We just got to denote what mean came from what group, what sample standard deviation came from what group, and what sample size is associated with what group, right? Now, it does not matter. It does not matter whether you say that X bar 1 is like a placebo group, and X bar 2 is the mean of, the manipulated group, or whatever intervention we're doing, right? Does not matter. It does not matter the order. Mathematically, the outcome will be the same. Since we will be working with this idea of differences, right? So sometimes it's convenient. Again, outcome totally the same. But sometimes it's convenient, when you subtract two things to get a positive number rather than a negative. Again, the outcome is totally the same. We just got to make sure that we're consistent with what we apply to what, right? So if X1 is the placebo group, this S1 also has to be the placebo group. The N also has to be the placebo group, right? Just got to be consistent. That's the big deal, right? Be consistent. So we got the sample means, got the sample standard deviations, sample sizes, right? Okay, and that's it. Same stuff, just double, right? So no biggie. So now we gotta learn about the nuts and bolts, right? Let's talk about this first. I kind of forgot. Which is totally fine. So in this world, we'll be here most of the time. Not because it's difficult to do these other two, The actual like t-test, the outcome, as far as the p-value goes, all you got to do if you want to do a one-tailed p-value, you just got to chop the two-tailed in half, right? We've seen that before. It gets a little kind of funky with the confidence intervals, because there's really only one, when you have a direction like this, there's really only one side of the interval that you care about. Sometimes it really does not matter. You can still do a lower bound, upper bound kind of thing for these confidence intervals with the directional hypothesis. Oftentimes, though, it might be something like, it might look like this, where it's down to negative infinity up to the upper bound, or vice versa, right? It's the lower bound up to positive infinity, whatever. It gets it gets kind of not complicated, but it's a couple extra steps we have to do. And I know that we've already seen one sort of situation. Do you hear those crows outside? Oh my god. So, I'll let you in on the life of me. Hey! Oh my god. There's a crow, a family of crows nesting in a tree across the street in a yard, and they're just cackling all the time, which is fine. Life is beautiful. But good lord, they're super loud sometimes. It's okay. What was I saying? Oh yeah. So I know we've already seen one example where we've done a confidence interval for a one-tailed question. That was just as an example. For now, we really are just gonna stick here. We're not gonna miss out on anything working in this world. They must be having some sort of argument, because boy, whatever. Okay, so anyway, long story short, two tails. Not going to worry about these two other ones so much. All right, now into the nuts and bolts. Since we're working with two samples, how do we handle this degree of freedom situation? Well, it's highly contested in the world of statistics. We're going to go with this one, though. We're going to go with the degrees of freedom is n-1 of the smallest group. Okay, so it turns out that in hypothesis testing, in two-sample t-tests, you don't have to have equal sizes of groups. They should be close to the same. There's not really a rule as to what denotes, too far away or whatever, or close or whatever it may be. But they should be close-ish. You'll see people kind of fudge that, and that's whatever. But we're going to go with this because it turns out that this is more of a conservative approach anyway, and it also happens to be pretty easy to do. So we're just going to stick with that, right? So if we have a sample size of n of group 1 is 20, and we have a sample size of group 2 that's like 40. Now that's pretty different, still, decent, whatever. We would go with the degrees of freedom based on this one, right? So the degrees of freedom would be 19, right? n-1, right? Of the smallest. Okay? That's the rule in this class. For this class. You'll see different things on the internet, and other, even other people in the department think otherwise, which is fine. That's what makes this whole thing really something. Okay. Now, degrees of freedom, we got that out of the way. The test statistic, very similar to what we've seen before, except we've just got times 2 of everything, right? Since we're working with this idea of straight up of like a mathematical difference, not like an English different. How are they different? We're actually looking at one minus the other, the actual difference between the two. All right, so that's why we've got that at the top. And then divided by, and this is our standard error, right, for this statistic, right? So it is S1, so the sample standard deviation squared, very important, squared of the first group divided by the number of things in the first group, plus the sample standard deviation of the second group squared divided by n2, right? So the number of things in the second group. Now we'll write this out. So S itself equals the sample Standard deviation. It turns out, though, that if you were to square that value, so you take f squared, that's actually equals something new that we kind of haven't really seen, but it's called the sample variance. Okay, no biggie. You could go your whole life with just plugging and chugging. That's totally fine in this instance. But do know that they do represent slightly different things. And that's okay, right? That is totally fine. You'll always be given this, right? This is a little bit easier to find anyway. And then once you get one value, you just square it and then divide it by n, right? Easy peasy. Okay, so we've got our t statistic for the, let me write it like this, the difference in the two means, independent means. Cool. So we've got that. That's not bad. And that's pretty much it as far as a hypothesis test side of things go. Our confidence interval also is super similar to the last example, where our statistic now is the difference of the two means, right? So this is actually some like value. We'll call it difference. Call it difference, right? So D, right? We can even just say some value D, right? The difference between these two things, plus and minus the t crit. Find it in the same way-ish as we did last time. Standard error is just the denominator of our test statistic, which is great. Very convenient for us, right? T crit. How do we find that critical value? Well, we just calculate the degrees of freedom, but the caveat being, at least compared to last time, we are now doing of the smallest group, okay? Degrees of freedom of the smallest group. More conservative approach. That's okay. And then you find the alpha that's given to you. It's almost always 0.05, 0.05. Very cool. And then you do the same process as the last time, right? Which is not too bad, I promise. And I'll show you a real example here in just a second after this video. But let's kind of see how everything works out as far as the whole process goes. Okay, so in fact, what I am going to do is I'm going to take a sip of water. Because boy, does my voice start to hurt after a while. You probably notice I do all of these all in like 1 or 2 days. And that's a lot of talking. So give me a second. Take a moment and read the question. And maybe pause the video and try it out for yourself. It is not too bad. You just got to kind of plug and chug. And then we'll talk about the conclusion here at the very end. So pause it. Check it out. See you here in a second. Dang. That was some good water. I think I've got the best water in Laramie. I don't mean to brag or anything, but I think I've got the least amount of lead in my pipes. All right. So, cool. All right, here we go. So the general idea of this study, and the general idea with these two sample t-tests, is we've got two groups, right? Most likely, one of them is getting some kind of treatment and the other one is not. The other one is acting more or less as a baseline, and we want to see what kind of effect that treatment has. Where in this case, if you read the question, I'm not going to read it word for word because that would take a long time. The idea here is that they're giving caffeine to one group and not giving caffeine to another group, and then they're essentially asking them to exercise, and then they're measuring just this respiratory exchange ratio. The amount it's a ratio between the amount of carbon dioxide you expire and the amount of oxygen that you inspire. I think that's what it is. It's been a while since I've done this physiology. So don't at me, please. But that's the idea here. So they're giving caffeine to one group, not giving it to the other, and they want to see how this changes, right? So the research question is, do we have enough evidence to say that caffeine, on average, changes your RER, your respiratory exchange ratio? That's the research question. You go out and do the experiment, and you find that, we'll just say that X bar 1 of the group. We can even say, actually, instead of 1, we'll just say placebo, right, equals 100.56. The S, right, of the placebo is, actually, let me not do that. S sub P means something else. Okay, so that is also found. That's also given to us. And then we know that there's 9 people. It's set up here, right? There's 18 total, 9 in each group, which is very convenient for us. So the ends are going to be the same. So I'll actually write it like that. And then X bar of the caffeine is 94.22. Now, just by this, ignore all of this. But if you were to just look at this, you would say, hey, caffeine brings it down, right? Or at least we saw that the average is lower. But then when you start to take into account the sample standard deviations, that kind of tells us that there's quite a bit of overlap between the two. So one standard deviation above this would be like 99-ish, right? One standard deviation above this would be 99. One standard deviation below this would be like 93-ish, right? So already we're seeing quite a bit of overlap, So we got to test as to whether this difference that we see here is actually true. If caffeine, on average, if everybody were to take it, right? If every male volunteer, if every male were to take caffeine, would their respiratory rate, exchange ratio, would it be lower on average, right, than people who don't? That's the question. That's the research question. So let's go on and actually test that claim, okay? So this is step 1. And then step 2, I spoke a little Portuguese there. Hope that's okay. Step 2 is stating our hypotheses, right? So, we can write it out mathematically like this, generally like this, where we might say that the mu1, might even just say this, that 1 equals, placebo, so nothing happening to them. 2 would be maybe caffeine, right? So we would say that the mean of the placebo group is identical to the mean of the caffeine group. That's our null hypothesis. In this case, our alternative hypothesis is that the mean of our placebo group is not equal to, it is not the same as the mean of the caffeine group, right? If we were to apply this to the whole population. Remember that we're trying to elevate everything back up based on our samples to the population, right? So this is our alternative, that these two are different, right? We can kind of translate the not equal sign into different, right, into English. And then our null is that they are the same, right? mu1 equals mu2, right? Okay. In English, we could say all this, blah, 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 blah. But since we're effectively making sure that the two groups are about the same, right? They're all males, probably young, probably pretty similar, nothing too crazy between each person. We could simply say that our null hypothesis is that caffeine has no effect on RER, that the placebo and the caffeine groups had an identical outcome, right? Even though we initially saw that the means were slightly different. Our alternative hypothesis, however, is the opposite. Caffeine does have an effect. We're looking at caffeine sort of as the sort of like medium, right, of the effect, right? Okay, so that's the idea. That is the idea. Let's actually get to making that test statistic, step 3. Okay, we've got everything that we know here, right? Placebo, so this is all of our placebo group. This is the caffeine group. Easy peasy, I've got it with the subscript placebo, subscript caffeine, so you know. Now, it doesn't, again, I was saying this earlier, it doesn't really matter which one you decide to subtract from one another. You just got to make sure you stay consistent with, your order of things. So X1 has to be X1, and then also has to be, the order here sort of matters, right? Ish. Kind of. Just good to keep everything kind of lined up like that, right? In this case, since the sample sizes are the same in both groups, this whole order here does not really matter so much. But the moment that we get, this could be like 10, right? Then that would have to be 10. The order then matters, right? Okay, especially in the denominator. Whatever. So if we just plug everything in here into the appropriate spots, let's do that just so you can kind of see. I'm going to do the larger number minus the smaller number, so I have a positive value. And spoiler alert, it's right here. But this is x1, x placebo, minus the group, the caffeine group. Gosh, that's going to be annoying. I hate it when it does that. Whoop. Okay. And then S, so I'm going to keep kind of this thing going on, right? It's going to be 7.7 squared divided by 9, right? So this is all sort of like sample 1 area. This is going to be sample 2 area. I recommend that you keep it kind of organized like that. Okay, and then the S, the sample standard deviation of our caffeine group is 5.61. I could be more delicate. 5.61 squared divided by then our sample size, n. It's just convenient that they happen to be symmetric, right? They happen to be the same value. That's great. Sometimes they won't be, right? So do keep track of that. And this is all underneath the square root sign, right? So you do a little bit of magic, and it turns out that you get a test statistic of 1.99, so like effectively 2. We'll leave it at 1.99 though, because I'm pretty sure I rounded it already. But that's what you get, right? You get 1.99. 1.99. Sweet. So what do you do with that value? Well, we just plug it into our t distribution tool, but first we plug in the degrees of freedom, right? So let's recall that degrees of freedom equals n minus 1. Put a star up here. It's the smallest n. It's always, in this case, in the 2-sample case for this class, it will always be the smallest n, which in this case, 9 minus 1 equals 8. And we put 8 right there. Booyah. Okay, and so that kind of sets up the curve for us, and then we just plug in our test statistic, 1.99, into the 2-tailed option, and then we get a p-value spat out here in the red box, right? And it turns out that p-value is 0.082 if we round it up. Oh yeah, right here, highlighted in yellow. So our alpha, actually I'm not too sure if it specified alpha. No, it did not. That's my bad. Alpha is, in this case, we'll just assume it's 0.05. My bad for not saying that. Okay, so that just means that p is greater than alpha. So since our p-value is greater than our pre-specified alpha, right, we fail to reject the null hypothesis. There's no statistically significant difference between the mean RER, between the population of people who consume caffeine and those who do not. At least based on our sample, we do not have enough evidence to say that the difference between the two groups was statistically significant. Okay. Now that's a whole lot of talk, right? That's a whole lot of talk. We're kind of close. We're kind of close to 0.005, right? It's just barely over, but them's the rules, right? Them is the rules. If we changed alpha, then maybe, right? But if we changed alpha, then when we make this confidence interval, we're also going to have to change that a little bit too. Now, I'm going to do this confidence interval, and I have it here for a reason, very similar to what we saw last time in the last video. We're going to do it for fun, just so I can kind of show you, right? So to find that t crit, and just to recap too, we found that there's no statistically significant difference between the two groups. That's the take home, right? No difference between the two groups. Even though we saw that the two means were slightly different, there's so much overlap between the two that effectively they are the same. Okay. But when we make this confidence interval, we want to find that t crit by plugging in degrees of freedom and then putting in our alpha. We're going to do a 95% confidence interval. So our alpha is 0.05. That spits out 2.306 as our t crit. We'll round that up to 2.31. Our standard error, this is just the denominator of our t-stat, okay, our test statistic. And then we just calculate the difference of the means, which is x1 minus x2, x bar 1 minus x bar 2. So 100 point whatever minus 93 point whatever turns out to be 96. Whoa. 6.34. Okay. All right. So let me write this out by hand first, just so you can kind of see. 95% CI equals the difference plus and minus RT crit 2.31 times the standard error. All right, so that's it. You can see it more elegantly written here, okay? Where the difference, we got the difference here, standard error, T crit, plug all of that in. You saw me do it just moments ago. And when you work out that math, it turns out to be, we can be 95% confident that the difference, let me actually write this out. Wait, oh yeah, no, perfect, I already have it. Sorry. I get so stoked about these kind of things. So this is our 95% confidence interval. Our lower bound, or we can be 95% confident that the true difference in the populations is between negative 1.01 and 13.69, okay? What do you see here, though? What do you see? Well, very similar to the last example. We have this idea that if mu1 equals mu2, then that difference is 0, right? There's no difference. What do we see here? Well, we see that 0 is contained within this confidence interval, right? So if we were to go out and do this all over again, there's a chance that the difference we would get would be 0. Straight up. Straight up no difference, right? 95% chance that it would be, it might be that, right? It might be that. Dang. That's really something, right? So let's kind of take a look, right? And I mentioned this in the last video too, but when we're working with differences, if the confidence interval for differences in means contains 0, right, it's likely that the p-value is greater than alpha. So we've already failed to reject. Oops. We have failed to reject H0, right? And we see that here, right? Our p-value is 0.082. We failed to reject H0. And then we have 0 in our confidence interval, right? Because the difference, if the difference between two things is 0, then that means there is no difference between the two, right? Because that means that they're effectively the same. So we could say that we're 95% confident that the true difference in the population means is between negative 1.01 and 13.69. Or effectively, if we were to do the math, mu1 minus mu2 would be 0. They're the same value, right? They're the same value. If we move this around, check it out. And that just so happens to be our null, to be our null hypothesis, which is pretty crazy that these things are so tightly related, right? So tightly related. I keep trying to write that H. Okay, right? Okay, so that's that. Let me then show you a better example, or another example, I'll say, where I take things a little bit slower and I do it all by hand, and then we'll be able to see what's really going on. So I will see you there in just a second.